Hello everyone. Welcome to this presentation about Hashstream. So we have been working on this proof of concept over the last couple of months as a vehicle to rethink content addressable serving of data. This is a minimal blueprint for trustless and efficient content delivery. Um, so we have this repo, Hashstream repo in my account in GitHub. And Hashstream is essentially a foundation. It's a conceptual exploration for builders, researchers, and system architects. Feel free to fork this repo, extend it, replace pieces of all the building blocks it uses. And with that, you are able to eventually build production-ready systems based with these ideas to serve content-addressable data. So essentially, having building blocks for running off-the-shelf trustless HTTP server for content-addressable data. Um, yeah, so to get up to speed before watching this video, I actually recommend that you have a look into this blueprint document. So it's in the repo, the blueprint markdown. It contains all the perspective and the vision behind it, and from the beginning on to the more technical part that leads to that. I will not cover this in the demo, but yeah, it's good for understanding what's coming. Um, for this case, we are going to go actually through a proof of concept that we built on top of Hashstream. So we have all these building blocks, and we want to easily deploy a server, a content addressable server with them, and prove that all of these ideas work. So we have another repo, Hashstream Infra proof of concept in Cloudflare. This is just a super simple repo. We are using SST for deployment. You can use like anything like Terraform, even Wrangler, or like what your favorite way to deploy something into Cloudflare workers or AWS. I mean, you can even run these in bare metal with a simple Node.js server as well. But here, let's focus on cloud-based repo. So essentially, with SST, you can, as a code, define what is your infrastructure, and we'll start to have two buckets in our infrastructure. So we have a bucket that stores indexes and a bucket that stores packs. You can consider packs to essentially be some piece of data, some bytes that are identified by their hash, which we call multi-hash. Inside these packs, they actually can have several other addressable pieces of bytes. So a pack can be in a way seen as a container that eventually may have several inside byte streams with hash that can be each one of them identified, as well as the pack itself. And then we have a server, which here we are deploying as a Cloudflare worker that has access to these buckets. And essentially, we want to see how easy it is to deploy and run a content addressable server that the only thing it does is receiving HTTP requests to get a CID. Let's imagine like you do a curl to this server, and in this curl you just provide the CID for the content, which is basically the hash of the content that you are looking for, and the server, without any discovery, without anything, just will look through the content, has access to its indexes and this pack store, and figure out, okay, do I have this content? Can I serve it? And serve it in a way that it's trustless, and the client can just verify the content, and basically not trust the server, but trust the content and and basically the location it got the content to, and see if the content is actually what it's looking for. So infrastructure is here. Then we need to actually create this Hashstream streamer based on the building blocks of infrastructure we just created. So we need the index store and the back store, from which we have the buckets. So we can essentially create some index store and the pack store from those. Note again, this is a Cloudflare workers environment, so we are using an implementation that abstracts this, but an index store and the pack store can actually be any kind of store. There are also implementations in the repo for file system implementations. You can also bring your own implementation with your own custom storage, because the goal here is that every single building block, it's something that can be changed, can be extended. The only thing it needs to fulfill is all the interfaces, so that every piece of the puzzle is pluggable, and you can just use what you want. You can even not use some of those. The goal is that everything should just work by like keeping the interfaces and the interactions between all these pieces working. So we have the stores, and then we need to have a way to actually get data from these stores, right? So then we have an index reader and a pack reader that the only thing they need is the stores. And then there will be this interface where the index reader interacts with the store in order to get content. All these interfaces are specified, by the way, in the main repo. We have specifications with all the different pieces. You can see, for example, in here, how the index reader would look like. I will not go through this, but as a hint, if you would like to build your own index reader or index store reader, this is what it needs to be into play for everything to work. Yeah, so we have the index reader and the pack reader. So we are now ready to have actually a server, which we call Hashstream, which then going back, what it does is as simple as I get a request. I'm a server. I get a request for finding out the bytes behind this multi-hash. I go through my index and I will see, okay, do I have any index records that somehow represent this multi-hash? If so, I will get all those records, and with those records, we'll have essentially the location where the content is. So, for example, this multi-hash we are looking for can actually be spread across several locations. For example, different packs, so different um, containers of sets of bytes. They can be spread into different ones, and then this multi-hash can actually point to all of them, or just one, or just to a single uh, byte stream inside the pack. So there are all the possibilities around that, depending on like how the index is built and written. So we have the hash streamer, and essentially we receive. So in this case, also actually worth mentioning that we are, for this proof of concept, implementing IPFS trustless gateway based on these building blocks. If you don't know what a trustless IPFS gateway is, you can go through the specification. But in short, it's using the IPFS protocol. How can we serve data trustless with the common route of slash IPFS slash and then a CID of the content, which with the CID we can obtain this multi-hash. Yeah, just get content from it. So here we get this hash streamer, and this function is also actually exported into the Hashstream utils package, and the only thing it does is wrapping the streamer around some HTTP response so that it can create the response in the format of the trustless gateway specification. Yeah, so pretty simple, like just create an hash streamer and it's ready to stream responses in content-addressable way. This is IPFS trustless gateway specific, but I mean, you could build your own. Imagine we will be talking about using Blake tree, for example, for hashing content. You can, if your indexes are properly prepared in order for Hashstream to read that data, like it does not really matter. So here you could return whatever kind of response it is that is a bundle of all the several pairs of bytes and multi-hashes that we'll go through in order to serve the content that was requested. Um, so with that in mind, let's show essentially how this works. So we have already a running server here, the development server using SST that is deployed with this worker on this endpoint. And I already have some data there so that we can essentially get data from it, right? So I will show you the buckets. So we have here the two deployed buckets with SST. We have the pack store and the index store. We have here two entries, so two different packs of data, each one of them like a octet stream with some bytes. And then we have the index store, which has a bunch of indexes, some that somehow will point to several parts of these packs. Um, yeah, so let's download to start with, get some content addressable data from the server. So let's imagine I share this link with you, and you could go and get some bytes based on this content address identifier, this CID that we have. So we have this curl command, and we want to get from the server this CID. We'll go into a segment into why this one, and we want to write it as a car file. This format car is basically something specific to the Trustless Gateway spec, so we want this to be read as a car. So if you see this Buffy Q2M, it will actually map to some of the indexes we have here, even though these are encoded as raw, so you don't see it directly, but essentially it would be the same exact. There will be the same hash here representing this index. So when we will do the get for this, what the Hashstreamer is going to do is see in all these indexes, if there's an index that represents this one, I will show exactly where it happens, but now let's just download some data. Yeah, so we are getting the data immediately just for those. And now we have 1522. So we have this car file that we obtained, that all this content should be trustless, and you can verify that it actually hashes to this hash that we just got the content from. So for this, we are going to use this tool called IPFS car. We are using car files for this because of the Trustless Gateway, but again, this is an option, not the only way to do so. So you can also write packs that are not car files. You can fetch different things. So yeah, it's really just sets of blobs that have bytes and multi-hashes by the end of the day, but then several layers of indexing around those. So IPFS car and pack, IPFS car, you can look for it also in GitHub as a way to unpack these car files into content, normal files in your file system, essentially. So by default, this IPFS car unpack already verifies if the content is actually the content you are requesting to. So it will go through the entire content and see if all dashes will map. So IPFS car unpack, and we want to unpack this one. Oh, actually, I wanted to unpack it to a file. Uh, yeah, to this one. Okay, so now we will have not only the car file, but also the unpacked version of this car. Yeah, we can open it just to see if it's really a file, and opens and so on. Yes. All right, so we have a file unpack download. So in the beginning of this demo, before I started, I uploaded one of these files into this service, so into the bucket itself. It was this image, this 15 megabytes image, and we can see if it actually is the same as what we just downloaded, this new image movie that we unpacked. Yeah, so there is no diff between them. They are exactly the same. So with that, let's maybe go back a bit into all the building blocks of Hashstream. Yeah, so we have the streamer, and the streamer reads from indexes and from packs that behind the scenes there is a store and eventually some object kind of storage. Um, so all these building blocks can be implemented in a way. We have implementations in this repo for all of them, but these implementations are suggestions. You can see if they fit your use cases. You can try them out, but we also are happy that folks just fork and extend them according to what are their needs. The only key thing again is to follow the same interface, and you can just plug and play and move as you wish. Um, yeah, so we kind of trusted that these indexes work, as I told you, but now let's maybe dive a bit deeper into those. For that, we also have a CLI tool in this repo, which we can interact with some Hashstream server. Like it can even be something you run locally. For some of these commands, you actually don't even need to have a server running, because maybe you're just operating locally and you have just some stores and you want to write packs there, or you want to write indexes from packs you already have, or maybe you don't even want to create content-addressable data, but you just want to create side indexes for those data. So yeah, you can use all of this. So the CLI is pretty simple by now. There is ways to write packs, extract packs, clear packs, add indexes, find the records of indexes in the store, or use kind of the streamer in a CLI way. To be clear, all the Ash stream is focused on reading data and essentially allowing anyone to deploy a lightweight server that can run in a Lambda, a Cloudflare workers. It's easy to deploy. It can be just a bare metal, simple server. So even though it's all about the reads, we identify that, of course, like if you don't have already these stars, you need somehow to write some files. So we provide also some toolkit that allows this, but the clear focus at this moment is on the reads. So what I'm interested in now is on the find records. So we fetch this content, but when we fetch this content, we actually used all these records. So let's see how did that actually work. Um, yeah, so this was the CID we used. I will go into a bit more details about this M thing and this store backend parameter a tiny bit later, but now let's just see, okay, we have this storage of indexes in R2, and we want to know like what are the index records that exist for this one. So we will go to find, okay, here we have. So the target CID, the CID we wanted, the store backend, the S3 like bucket. We found this record. And we also found, so this record is just a blob that represents some data for this CID. But we also have some other bigger piece where basically we have this CID pointing exactly to the entire content of this, because as we can see now, there are a lot of subrecords, which essentially means that this content we looked for is actually split into different kind of eventually even locations. So we have a first subrecord, which is a pack. Which, if you are familiar with IPFS terms, can be a car file. And so this can be the root CID of the content. So we have some content. This content may be charted in N kind of packs or car files, which you see here, 1 year and 1 year. And then even inside these packs, we may have some kind of blobs. So we want to be able to fetch either like a single blob like this one, but also we maybe just want to fetch the entire pack, or maybe we want to fetch the entire content. So like there is all these layers that when someone writes the index, you can write this index in a way that all the data that may be queried is there, and you can just see where it is and fetch it. So let's imagine we want to fetch this blob. We will see, okay, where is it located? It is located in this pack and then in TE, which is essentially this pack. And it is in this offset and length. So you can just pass this location information to a pack reader, and the pack reader can immediately get the bytes that represent this individual CID. But at the same time, if we would want to get all the content from this, which was what we requested, We can. So essentially, what the streamer is going to do is getting these all these records and just pass all of these to the pack reader so that the pack reader streams back every single one of these blobs. Yeah. So it will go through the index and okay, so I need to get offset from year to year to there. It will do like a multi-batch request to get all the batches associated with one record and then the other one and so far. So that's how we could get all this data. Um, if now, for example, we would go to IPFS car and use another primitive they have, which is seeing about blocks. So we have this car, and we can see all the blocks that are in the car, and all the blocks that are in the car should actually map exactly to what we have here. So this 2M, 2M, JQ, JQ, and so on. So all these IPFS car blocks are inside the records, and they are like each single individual unit inside the entire pack. Um, so going back into this environment and the star backend, we are in the CLI currently target this remote storage. So we are using a star backend, S3 like bucket. And so when you interact with S3, you need some kind of environment. So you need to have, of course, credentials to interact with this bucket and so on. We also have this document star backend usage where you can create an environmental variables kind of file and yeah, essentially file every single environmental variable that will be needed to interact with the bucket. And then you're ready to go, and you can write, for example, some stuff into the bucket, or you can find these records like we did. Everything is yeah, really possible with interacting with the CLI to a remote environment. But by default, like if we just don't set the star backend, the only thing that is going to do is rely on the local machine. So let's imagine we want to actually run this in a local server. We don't want any S3 kind of thing. So in this case, we will Hashstream CLI will keep some state of having a temporary folder where you have your packs and your indexes, and everything goes there. And when something is written and when something is looked, it will see those stores. So it's the same, but in a different kind of storage implementation. Instead of S3 like, it would be a F file system like. Yeah, so even though this is then focused mostly in reads, we have, as I mentioned, this toolkit to also write content and to index content. It is not required in any way. It's actually optional because we want to focus on making it possible to do reads in a way that if folks already have packs and indexes, they can just easily use this. Because if you actually have packs and indexes, you just need to run a streamer and eventually create some simple adapter for your pack reader and the next reader implementation in a way that it just exposes exactly in the same way the indexes and the packs as the interface specifies. But maybe you are in this environment where you already have some packs, maybe you have some car files, but you don't have indexes for them. So in this case, you can also simply just generate indexes with the indexing toolkit in a way that it fits the indexes that are used here, or you can simply also just create your own indexing strategy, indexing notation, and have an index reader that can interpret that in a way that it can give to the streamer. Or perhaps you just have raw data, and if you have raw data, you maybe want to convert it to a content-addressable data, so you can use the pack toolkit to transform into packs, eventually the index toolkit to generate the indexes. By the way, if you use the pack toolkit, you can also opt in to use the index toolkit at the same time to optimize processing. But I mean, in the end of the day, you may even decide that no, like I don't want to do a data transformation. I want to just retroactive add content addressability to my data. So you can create an index writer strategy where you create indexes that point to byte streams from your data, but you don't really need to change the data that you already have at rest. Um, so let's see a bit of this in action. So we will want, in the same way that I previously wrote this file we were seeing here, we want to write a new file. So we have I previously added this file to the bucket, so now I will add one more. So again, we need to put the environment to make sure that we can communicate with R2, and then we want to do a pack write. And we want to use not this one, but the 8926. We have here the pack size set to around 10 megs, if I'm not wrong. So essentially what this means is that we want to shard this pack into at this maximum size. This is optional. This can use the maximum. So this is a balance that everyone needs to see according to like what kind of data they have and what fits better for efficient proper purposes. Then use store backend and your index writer. So your index writer is how does the index are created? Do you want to support queries that only target some levels of your data, or do you want to actually every single blob to be addressable? So all of these, of course, has different kinds of costs. If you want all your data to be addressable at the more atomic level, you need to have much more indexes, which will be more expensive. But maybe you need to do those kind of queries, considering, for example, it would be in a bit swap kind of environment, running a bit swap protocol. But if you just want to access the root of your content and you don't care about all these pieces in the middle in the lifts, you could potentially just use like a multiple level that just points to the top. So here we have two index writer implementations. I'm just passing all so that all types are used for the index writer, but any new index writer can be created. And for instance, an index writer to write indexes based on content that is not transformed is something that would be really interesting also to add at some point to this suite of toolkits. So let's write this data. Um, so this is a 39 megabytes file being currently added. Let's see, taking a bit more time than I would be anticipating. Okay, I hope this is going. Yes, okay. Maybe it was too many shards. Okay, so we wrote this data. So like this took so this needed to handle several things, right? So it needed to transform this data into a pack or a set of packs with a maximum size of this, which it was created. So 1, 2, 3, 4, 5, and also transform this data into some kind of encoding data. Here we are just using the defaults from IPFS, UnixFS, which comes with the car files and so on, but this is just an implementation detail that is completely transparent for the server. And we wrote indexes both at this level. So if you can just query for the containing CID or for packs, but you can also query for every single one of these as well. So now, for example, if we would come here where we previously would have these ones, now we should have much more indexes. Yeah, in the new pages of indexes. And we used to have two packs. Now we should have, so 1, 2, 3, 4, 5 more, which should map to how many we had here. 1, 2, 3, 4, 5. Yeah, so this is how potentially someone can write data to a bucket. This process, as you see, is completely independent from the server that is running here. I could even have stopped it. So the server only purpose is to read the write simply writes to this common storage that is used both for read side and is some storage unit that is at rest, ready to be used to also to serve content. Um, that is all for now. So Hashstream is a foundation, a conceptual exploration for builders, researchers, and systems architects. Please feel free to fork it, to give feedback, to replace pieces, to pull requests with new implementations of pack storages or new readers, new index writers. Yeah, we want to work together to actually figure out what is the minimal way to have off-the-shelf trustless HTTP server where you can just plug simple building blocks and in some moments you have a server running and you can just serve some content-addressable data out of your server and you don't need to handle any content discovery and so on. Just need to know what content you're looking for, a location where the content is, and you can just fetch it, verify it locally with the client, and you are ready to go. Thank you so much.